Hello, welcome to the AWS webinar, Computational Fluid Dynamics on AWS. My name is Scott Eberhardt. I'm a worldwide public sector Principal Solutions Architect Specialist for HPC. I'll give a little bit more about my background, which I think is relevant to this webinar in a minute. I want to first lay out who's the targeted audience. Primarily, it's for CFD practitioners. Next, the CFD support staff who supports those people. Solutions architects who want an introduction to CFD workloads, and also vendors of CFD codes who want to find a way to maximize or improve their visibility and get greater market. My background, I actually come from an interesting background being in IT right now, and then I spent 25 years as an aerospace professor in various places. I worked for Boeing in product development. My current position, though, is an HPC specialist. I come from this as an end user, like many of you, as opposed to coming from IT and then specializing in HPC and CFD. So my background actually is CFD. So which industries use CFD? We've got the vehicles. My background, aerospace, I dealt a lot with Boeing airplanes and spacecraft. Wind and weather, combustion, engines, that sort of thing. Many sciences, medical, more people are using them to study the flow of body fluids like blood. Oceans, I've met people who use the same algorithms I do, modeling groundwater. Energy, turbines, oil, civil, HVAC, thermal. A lot of people use CFD for modeling ventilation systems and hydraulics, and anything that interacts with a fluid. Fluid can be plasma, air, liquid, anything that interacts with a fluid. So what we're going to cover today are some CFD processes and why AWS. That's sort of a level setting for because of the broad audience that I expect are watching this. How to set up a simple single node CFD infrastructure. How to set up a cluster to run a large CFD applications. This will, of course, I won't be able to show you the entire demo. I've pre-baked some things so that we'll be able to move along and get this webinar completed in the time allotted. We'll go through some CFD best practices and also discuss some CFD tools that are available. I don't want to spend time as trying to talk about which one is better or anything. I have no intention to offer opinions on such subjects. This is just to demonstrate what is some of the things that are available on AWS. Okay, so let's first do some level setting. Talk about the CFD process. When people talk about CFD and think of CFD, so often it's only the solver of solving the partial differential equations for the fluids. But there's a lot more to CFD, and so I do want to talk about that. We have multiple steps. Geometry cleanup. First of all, geometry is usually coming from some CAD package that is not adaptable to the CFD process, and there has to be some manipulation there. Solutions. The solution is always an iterative process. The first solution is really just to guess, and you have to get to the post-processing step sometime to see where you made a mistake. Might be in your geometry, might be in your mesh generation, might be in the solver. And the solution is only as good as your geometry or the mesh or the solver settings. Now, some vendors, some CFD applications have good geometry cleanup tools that make it easier. But then it also depends on what kind of fidelity you're looking for. If you turn over your geometry cleanup to an automated tool, perhaps that might be a problem for you if you're trying to capture details of a laminar sublayer. So it's all up to an individual what tools they want to use and how they want to use them. The wonderful thing about AWS is that we have lots of tools that work for various steps in this process. And by tools, I mean we have GPUs that you can use for geometry cleanup. The best place to do that is typically in some sort of CAD package that allows you to move lines. Like a typical problem might be two lines that are supposed to be coincidence are offset by, 10 to the minus sixth or something. They have to be together in some packages, and so you would move them to co-locate. Other packages will clean that up on their own. Mesh generation. These typically require large memory or large memory per core. So mesh generation, if we want to do it optimally, we would like to have a computer that fits that. Solvers, the speed is typically limited by memory latency, and there's always a balance between the number of processors and the mesh size or cells per core. And we'll talk a little about that more later. And then there's the post-processing, which usually is graphical and again requires lots of memory and fast graphics. And so GPUs are great. In AWS, we have a variety of instance types or node types, each one having the ability to map it to the size of your problem. And we'll see a little more about that later. So here's an example of sort of the first step geometry cleanup mesh generation. This isn't so much cleaning up an error in the geometry as it is just cleaning up the surface by making a tighter mesh. You'll notice the lower one has a lot of faceting. If you were to try to get a high fidelity solution and solve for the boundary layer on that, you'd get complete garbage. Mesh generation, this is something that has taken years to perfect, and now there are many tools. I'm always amazed. I've been at this since the 1980s. The mesh on the right is what we call structured. You can see the nice structure in there. The mesh on the left is unstructured. Most codes today are leaning towards unstructured just because the meshing is so much easier. I should mention that these steps that I've just referred to used to be and still are kind of the lion's share of the human work that's involved. There's a lot of tools that have improved this, but I always go back to a benchmark of one of my colleagues when I was working at NASA back in the early or mid 80s. He did the first full space shuttle simulation. Generating the mesh for that took 6 months of his time. So if the solver is only taking a few days, the time was all in this geometry and mesh generation. And while we've improved on that, there still is most of the manual labor that goes into any solution. When we solve a problem, for example, in this aircraft, we're typically solving a whole bunch of problems with different conditions. So in this particular example, we're looking at lift as a function of angle of attack, the angle that the airplane makes with the air. And each one of those points that we see there is a solution. And that can take anything from hours to days to weeks in some cases. So the solver really does all the compute work, and that's why we focus on it so much. It's not necessarily the most intensive time in terms of the human input, but it is the most intense time in terms of the computer, and probably the costliest in some ways, although, depending on what your engineering time costs, maybe not. Many solvers are available, and I apologize in advance if I've missed someone's solver. I didn't intend this to be a complete list. There's many different flow solvers out there. So why AWS for CFD? I mentioned one, which is all our instance types or node types that can be optimized for different steps, but also a big factor is really our scale, our agility to scale to many nodes if necessary, or to run many jobs in parallel. Running jobs in parallel, we'll see in the next slide, is actually what one of our customers does and saves them so much time, and that's engineering cost in that time savings. Uh, with running many jobs in parallel, we can eliminate HPC resource contention because you're not having a bunch of people jump on a computer and sitting to a cluster and waiting in a queue for their jobs to run. Instead, you submit or you create a cluster for a job. Think cloud is very, very different than an on-prem situation where you've got a fixed size. In cloud, you can scale to virtually as much as you want. I'd like to say infinite. We're not an infinite resource, but we are large. I use an example of one of my colleagues who did a proof of concept and was able to launch 1.3 million cores in the spare capacity in the London region. There's a blog post on that if you want to look it up. So there's no queue. You basically create your cluster, submit your job, run your job. It's done. You can then delete your cluster or use it for another job if you want. But you can also run multiple jobs at a time, running multiple clusters at a time. So that's an easy way to expand on AWS. Use it when you need it. You also can launch the right size cluster and the right resources for your job. You don't have to have a machine that's a compromise, that's a balance between multiple workloads that might involve fields far away from computational fluid dynamics. Instead, you can actually optimize your cluster for your workload. And in fact, that is actually one of the ways that people save money is by having an optimum cluster for their workload. On AWS, you also only pay for what you use. So this is interesting that people have a hard time in the on-prem world really feeling or understanding is that it costs no different to run your 10 jobs in parallel as it would to run them serially. So you might as well run them in parallel and get the job done. TLG Aerospace, an aerospace company based in Seattle, does exactly that. They used to have to run things serially, and now they can run it all in parallel. The engineering cost savings is huge because instead of having to wait a week for results, they get the results overnight. This is a huge, huge improvement. You can Google TLG Aerospace on AWS and read all about their success story. With AWS, you have the ability to experiment on your cluster. And by that, what I mean is look for something that might get you a solution faster or cheaper. You can play around with different instance types to figure out if one is better for your job or not. And because you're not buying hardware that's going to sit in your laboratory for the next 45 years, you can experiment without fear. Typically, I might run through 3 or 4 configurations in a morning. You can start and stop your instances, and what I tend to do is have a cluster where I have 0 compute nodes, and then when I run a job, it just automatically scales, and we'll talk a little bit about that later. We also have spot pricing, which can be difficult for CFD for long-running jobs, but maybe it's something that you can use where you have lots of savings because using our spare capacity. Of course, by using our spare capacity implies that they're spare, and on demand would, of course, get priority. The nice thing, too, about going to a cloud solution is that you get continuous updates and you don't have to be responsible for them. So for example, at AWS, you can pretty much be assured that you'll have some of the newest equipment that's out there soon after the suppliers come up with it. Network updates, storage updates, we are always coming out with new services. So important enablers are compute performance. We have different types of CPUs from Intel, from AMD, ARM. We have GPUs. We have FPGAs if you want to really get creative and do your own programming of your field programmable gate arrays. Memory performance. We can change you can change instance types to get different amounts of memory per core. Our standard compute is fixed at about 4 gigabytes per core. We can go up to 16 gigabytes per core for higher memory instances, or we have some crazy nodes that have up to 12.5 terabytes, but those wouldn't really be recommended for our work for CFD. Network performance, we have different options for network performance, and we've done a lot to improve our network latency. We have something called the Elastic Fabric Adapter, which is new in this last year, that really puts, in terms of CFD, it puts us up in the supercomputer category for large computations. Storage performance includes including shared file systems. We have a new file system that's Lustre, a Lustre file system called FSX for Lustre. It's fully managed file system, and it takes care of all of the headaches of having a Lustre type file system on a cluster. We have a new product called Parallel Cluster, which handles the job management and automation of launching a cluster, and it really puts everything into a simple config file. We don't have time to go through that today, but there are blogs on it, and there's webinars, and I encourage you to look that up and follow that, and it's fairly easy to launch a cluster today. Remote graphics and interactive applications. We have a product which I'll be showing called Nice DCV, which is really a great way to enable you to do your post-processing on the cloud. And then we have support for licensing. And the nice thing about going to cloud is that you can scale. So you can run many workloads on single instances. This was something that, coming from the aerospace industry and dealing with very large calculations, was sort of a surprise to discover how many workloads, and probably the majority of CFD workloads, can actually run on a single node. And we have nodes that go up to, in our CFD enabled world, I would say we can go up to 48 cores on a single node, which is a new Intel node. And I think that that's probably handles probably 80% of the CFD workloads that are out there. So if we do some cost and performance optimization, you can actually get some significant savings. A lot of times, if you're not careful, you can design or build a poorly performing cluster or pick the wrong instance type, and it doesn't take much to do some tweaking to find the right performance. And then there's a much more detailed performance if you really are concerned. And we'll talk a little bit about that later, but I'm not going to get into the real nitty gritty. It's too little time to do that. And sometimes if you try to look at how much is it going to cost per hour, that can really be deceiving. First of all, high cost instances like our GPUs may look like they're really expensive. But one of our partners, a company called Zenitech outside of Bristol, ran some calculations on one of our P3 instances, which has 8 V100 NVIDIA GPUs, and found that it was equivalent to 960 cores on our Broadwell Haswell family of C4s. And so you're talking about one single instance versus an entire cluster, and the P3 instance was faster and thus cost much less. Also, if you match the memory with CPU better, you can get better performance, and that can lower cost. And typically, the newest family instances are going to be faster than what you're used to, mostly because what you're used to might be kind of old. I've got some benchmarks later where we've run our OpenFOAM out to 2,000 cores, and are much faster than Archer, which is the UK supercomputer that's getting dated. Okay. So if we're looking at single node CFD, local accuracy typically is not going to be critical in this case. I'd be surprised to see many people doing single core CFD when they're interested in details of the boundary layer. or dealing with flow separation, like we do or like we're concerned about in aerospace. Typically, I would say this is just approximate. That's going to be less than 10 million cells, and this is going to be solver dependent. So depending on your favorite solver, this will have, what we will work on a single node will probably differ. Huge advantage is there's no network bandwidth or network latency issues. Although in the reality in CFD, we don't really see that as being a terrific bottleneck for medium size and even up to some large size jobs. And we'll see some examples later. So examples where this single node CFD may work as in, flow ventilation, where you're not concerned about the boundary layer, duct and hydraulic line flows, and sometimes for optimization or scoping exercises, where you don't really care so much about the accuracy at that point, but you want to get reasonably good answers. So I'm going to do a quick demo here. We're going to use OpenFOAM. OpenFOAM is a very popular open source code. It's available for free if you want to download it and compile it yourself. What I'm going to do here, and this is just kind of a notional example, and is I'm going to use what we call an AMI, an Amazon Machine Image. Many vendors have solutions that are available for you that are purchased or licensed through an AMI that you can then use in very much the same way. And I posted the AMI number here, or ID, which is, you don't have to worry about that. Okay, so let's go and I'm going to try to find the right window here. Okay. Okay. So one method for getting the OpenFOAM single core image AMI is to go through CFD Direct on the marketplace. So some of you might not be aware, but AWS has a marketplace very much like the retail Amazon.com, where vendors can sell their wares or produce their wares, and many times there are freebies on the marketplace. Universities sometimes put things up, and so you might want to take a look around and see what's on the marketplace to find out what's there. But CFD Direct has a OpenFOAM solution. Now, I've already gone in here and requested a license. The first thing you have to do is this yellow button here that says continue to configuration. The first time you come here will say something like request a license. After you do that, it'll come to this window where you can continue to configuration. Okay, so I'm going to click on that. And it basically sets up what I want to do, what version I want. This is going to be 7.1 from CFD Direct, 64-bit machine image. The region, I want to go to Ireland, okay, just because that's the local to me in London. I could use the London region. I prefer Ireland just because it's one of our larger data or regions. And then I'm going to go to launch, and what it will do is it'll give me some review, okay, and it will warn me about some of the, or it'll give me some updates, some various things, and then I can just launch, okay. So I've already launched one, and so instead of launching another, well, actually, no, I do need to go through some steps here. I forgot, because I want to show the, I want to show some of the things that we want to do here. Okay, so I want to launch through EC2. CFD Direct, by the way, if you go to their website, they have their own portal, so you can actually launch and have a CFD Direct command line interface, and you can do things like launch clusters from there. It's a very complete interface, but I'm just going to launch through an EC2 instance. And what this will do would be provide a node that I can log into. The uh, once you launch, the first thing it will prompt you for is what kind of instance you want to use. So this is where you get to choose what particular node type, how much memory you want, whether you want a compute node, a high memory node, or whatever. In this case, I'm going to just do a very simple, small example, but I want to go to our compute node. So I'm going to scroll down this page until I get to my C. You notice that the different sizes here, they're kind of like t-shirt sizes. I'm not going to go into much detail, but I encourage you to look up and understand our naming convention. What I want to do here, though, is I want to use something called a C5.2 extra large, which has 8 vCPUs. And I do need to explain for people what a vCPU is. It's a virtual CPU. It's basically a thread. And Intel uses hyperthreading. And so this represents 8 hyperthreads that are possible, but there's only 4 cores. Each core is capable of 2 hyperthreading. They call this hyperthreading, and normally in CFD, we encourage people to disable it. And the reason is that the chips are designed to do massive amounts of work in parallel, and if you have different types of workloads, different parts of the chips are going to be exercised by the 2 threads. But if you're doing purely computation, as you would in CFD, they're both threads would be using the same pieces of the CPU, and therefore they'd be conflicting. So it's usually beneficial just to turn one of them off and just to have a single thread through each CPU. So when I see this, I automatically divide this in half and know that this is 4 cores. And I'm going to run a small problem. So it's 4 cores with 16 gigabytes of RAM. So I've got 4 gigabytes per core. And I'm going to review, and I'm going to launch. Okay, and I can just push launch here. But instead of doing that, I'm going to go into what I've already launched before, and we'll go look at that. Okay, so after I've launched, I now have an EC2 instance or a Linux box that I can SSH into. So I log into this. I'm on a Windows machine. You can use PuTTY. You can use MobiXterm. You can use a variety of products that give you a Linux interface. If you're using a Mac, you've got that Linux interface automatically. But so you log into your head node, and if I look here, I notice that OpenFOAM is installed. Okay, OpenFOAM is available. And if you'll excuse me for just a minute, I'm to save time, I have put open, or I have created my commands in a file so that I don't have to type them out for you. But here's the OpenFOAM installation. It's all available for you. And so the nice thing about using a marketplace solution is that everything is installed. Nothing for you to do. It's ready to go. Okay, so I'm going to move to a run directory. Okay, so now I'm in a run directory, which right now has nothing in it. Okay, I am going to copy from the tutorials. I'm going to copy the tutorial wind around buildings. I'm also going to do a little bit of a cheat here. So we're back. We cut away because the solution takes a little while, and the solution ran. So now we're going to run Parafoam. And I'm doing this on purpose, in part because I want to show you the advantage of a product that we have called DCV, which will make this so much faster. And so right now we're launching through an X window environment, and it's going to be rather slow. So when I get to the next round, when we start on a cluster, we'll see that that we can manipulate it much faster. So this is, again, taking time. While this is going on, let me just go back. While this is loading, I'm just going to go back and to the presentation just a little bit and talk a little bit about OpenFOAM for those of you that are unaware of the product. It's an open source suite of CFD tools. It's got incompressible, compressible, multi-phase flows, reacting flows, unsteady flows. I mean, it really it covers the gamut of fluid mechanics. You can also add custom modules, and that's one of the things that really is powerful about it, is that the open source community will allow people to actually work on the code and add their own customization. Multiple time integration methods, multiple convergence acceleration methods. And I do want to spend a moment talking about that because this can be true of all codes. It turns out, depending on how you scale your problem, in this case, you're doing a single node, so it really doesn't matter which convergence acceleration method computationally it might for your solution, but when you scale to many, many, many nodes, it turns out that if you use a convergence acceleration like multi-grid versus a conjugate gradient, those two can behave very differently. You might want to actually run them both at some point, experiment, and see if one is going to give you a faster solution than the other on the infrastructure. Normally, we don't think of that because we're so used to knowing that one's going to be faster, but that's because we're using the same infrastructure over and over and over. So let's see, I'm going to go back to the previous solution. I'm still waiting for it to launch. We might not watch pair view in this demo. Oops, there we go. It's coming up finally. Okay, here we have it. Okay, well, we can see it took a long time. That's really was my point. If I loaded it up, we would find the manipulation is rather slow. It's rather cumbersome, and I'm not going to do it in the interest of time. But we will look at pair view in a few minutes from another mechanism. So let me just move on. Okay. So single node CFD for optimization, when thousands of runs are required, you might consider spot instances. So spot instances have the problem that they can get disrupted by a on demand. If that happens, your instance will terminate. You can hibernate your run. If you're doing single instance runs, if you're doing thousands of runs, you might just want to restart it. I call it a spot tax. About 5%, depending on the instance types of spot instances, get terminated during the course of a typical run. So if you're running 100 runs, 95 of them will complete normally, and you might resubmit 5. It's also very there's a temptation to add more cells to avoid launching a cluster. In other words, cram as much as you can into a single node. The problem you get there, of course, is that you might stretch beyond the memory that's available. And so that becomes a problem. And launching a cluster really isn't that difficult with our product parallel cluster. You also have to remember to run in parallel, which means you're going to have to do an MPI run or scheduler, or if the code is written to handle OpenMP and do multi-threading, that works, but you have to remember that you got to run it in parallel or it will only use one core. And that is unfortunately typical of a lot of inexperienced users. So I encourage you to make sure you're running on multiple cores. And then pick the appropriate instance type. So here's some examples of instance types. These are non-GPU. I'm in the interest of time, I'm only showing some of the ones that are most common for CFD. Our C4 is a last generation that has up to 18 cores. Our C5 is up to 48 cores. And again, as I said, it's 4 gigabytes per core. We have something called a C5N, which is a network enhanced or network specific C5 instance type. This is the Skylake, Cascade Lake Intel family. The N means that we have up to 100 gigabyte per second bandwidth. We have the M5, which is sort of a general purpose, has more RAM per core, but it actually is not optimized as well for computation. The R5 is a high memory core. This is where we get 16 gigabytes per core. And then we have a super fast 4 gigahertz Z1, which is 16 gigabytes per core, really fast and much more expensive. But perhaps the cost is saved by the fact that you're not going to run as long. So these are just some instance types you could play around with and experiment with. Okay, so now let's talk about clusters. So generally, when you start going to larger problems, numerical constraints creep in, and you run into the CFL limits. For those of you that are CFD backgrounds, you'll know what I'm talking about. And larger grids sort of require smaller time steps. Thus, the compute time grows very non-linearly. It's best when you grow your cluster to keep the cells per core near optimum. And how do you find the optimum? Experimentation. So typically you might want to start at 100,000 cells per core, maybe scale out to 50,000 scales per core, and just see where you start getting into latency issues that might slow your code down. If you go too high, like 200, 300 cells per core, you might start running into memory latency issues. So you have to play around with what's the best. You might consider a shared file system. Our new FSX for Lustre is very desirable because all your data is in one shared file system instead of having all the traffic go to head nodes. We're going to now launch OpenFOAM in a parallel cluster. Parallel cluster is a very powerful cluster management tool that we introduced about a year ago as a service. It used to be more of an internal, well, it was available to everyone. We call it CFN cluster. Parallel cluster is our now supported service. And here's a blog that you can reference that is parallel cluster with FSX for Lustre. So all this is now built in, very simple. If you go to that link, and you can certainly Google parallel cluster and FSX, and you'll find this. When you do that, you'll find simple instructions on how to do this. And really, it's sort of amazing how quickly you can launch a cluster that's very similar to what you might have on-prem today, only with brand new stuff. Building OpenFOAM, many different ways that you can build OpenFOAM. Just go and Google it and you'll find probably half a dozen repositories and services, and you've got CFD Direct. You also have the ESI version. It's available many places because it is open source. So we encourage people to do what they're most comfortable with. Okay, so what I'm going to do is, or what I have set up already, is launched a cluster using, and then once it's launched, I've created an OpenFOAM installation using SPAC. So I cloned SPAC, then I installed OpenFOAM, and that gave me the ESI version of OpenFOAM, which is version 1906. All right. So I'm going to move now to an alternate window here, where I'm going to show you what I pre-baked. So I launched a cluster. So this is the command line here. It's a command line that I launched that basically said, I'm going to create a cluster named CFD, and I'm going to use a CFD config file. Again, because of time, I'm not going to go into that file and talk about it, but I will tell you it's about 30 lines of simple text. In there is everything from enabling our elastic fabric adapter to launching an FSX volume, to deciding what instance types to use. In this case, it was a C5N 18 extra large. All of that's in that file, fairly straightforward, and you can find many references online to how to do that. Okay, so if let's see, this is my cluster here. So I'm in a cluster, and parallel cluster gives you kind of a really cool thing that you can do, and this is a trick that I use. What it does is I start with no compute nodes. Why do I want no compute nodes? Because I don't want to pay for them. I can set up my FSX file system. So let's go there, where I've got OpenFOAM installed. So we can see OpenFOAM there. I also have something called Nice TCV installed. I have some examples that I've run. So all the stuff is available on my FSX volume, which is a managed service, as I mentioned, but I have no compute nodes. And I don't want the compute nodes because I don't want to pay for them until I submit a job. Now, we're not going to be able to do that just because of time constraints on this in this webinar. But if I were to launch and request, let's say, 1,000 cores, the auto scaling within AWS's infrastructure and part of parallel cluster and whatever scheduler I use will automatically spin up compute nodes to match that. And I don't even have to do that. I don't have to manage it. I just run this like I would any on-prem head node, submit my job, sbatch, qsub, whatever, and launch my job, and it will pick out and grow to that size and pick out nodes that it needs in order to fulfill that request. When it's done, those nodes will recognize that they're no longer working and they'll start turning off. So I don't have to pay for them. And this is really, really pretty cool, I think. Okay, so I've managed this run, and in this case, I for the demo, I didn't spend much energy here. I apologize. I didn't want to run big jobs, so I ran the same wind around buildings, have my run completed, and what I'm going to do is launch something called DCV. So I'm not going to go through DCV again. There's blogs and stuff that in web pages that show you how to do that. But DCV, I've got two methods that I can call that will go into my head node, or if I choose, I could actually launch a separate node, a graphical, a GPU-enabled node, and launch DCV, which will then allow me to do all the graphics rendering in the cloud and only display. So in the left window here, I have I've gone through as just a simple web address. So this is just a web page. And on the right, I have a client server on my laptop. So let's go through the web page. I'm going to reconnect here because in my in my time that I was off waiting, it disconnected, and I'm going to make this screen large. Okay, so I've already launched Parafoam, or Paraview, sorry, so that we can have a little time here to explore it. And unfortunately, my window isn't that big. But anyways, here's this solution, and it allows me almost instantaneous adjustments here. I mean, I can play around with this, and if I had a very complex geometry, this would allow me to manipulate it and do whatever I want and totally interactively. And so DCV is a really great product. And I realize I don't have my mouse with me, so I can't do everything I want to do very easily. But this is just an example of DCV. We didn't do the X Windows version of this before, but you can take my word for it. This is much more responsive, and this is how DCV works. And it doesn't matter whether I do this on the web, so this is just a web browser that I've pulled up, or if I use the client on my laptop. Okay, so installing any software is, it's the one thing that unfortunately takes a little more time, but again, vendors of various software packages help you, and you can or have tutorials and stuff that allow you to do it quickly. There's an enormous amount of stuff online. Okay. Um, so here's an example of some scaling, and this shows our C5N using a 100 gigabit per second network. We had not yet benchmarked it with our Elastic Fabric adapter, which lowers the latency, but you'll see going out to almost 2,000 cores here, we're very close to linear scaling. This is the optimum scaling that you can get, is this orange line here. And so OpenFOAM's doing quite well, and part of this is the ability to use FSX. So cluster best practices on AWS, one of the most important things is you want to use something called a placement group. If you use parallel cluster, there's just a simple call, a simple line of text that you would input a command that basically enables the placement group. A placement group grabs all of your nodes in a close proximity together, close proximity to each other. The last thing you want in a CFD calculation is to have one node over in the other end of the data center, or even another data center, because that latency then will become your slowest node, and you will see that in your calculation. So we have something called placement group, which says go find all the nodes that I want in a near region. Within a few racks if possible. As I said, you want to experiment to find the optimum number of cells per core. So you want to run the same job maybe a few times to see, to look at its performance. Important when you're doing MPI kind of runs or parallel runs is that you partition the mesh equally. It's very easy sometimes to make mistakes in partitioning the mesh and having some very small zones and some very large zones. And of course, the large ones are going to take a lot more time to compute. When I was doing my dissertation back in the early 80s, I had partitioned, this was actually before parallel computing really even existed, but I'd broken up my domain in two very mismatched size, where one node had one part of the job took 1/10 the time of the other, which meant that, of course, I was being delayed by the fact that it was imbalanced. You need to make sure your input file for those parameters are correct, or sometimes using blocking for different mesh generation methods. The blocking will actually dictate how it's going to break up the code into multi-processing or multi blocks. So you'll want to make sure that you balance that as much as possible. And then, as I mentioned earlier, with the hyperthreading that Intel has, you'll want to disable that. So those are general best practices that we have when we deal with cluster CFD. Now I want to talk about some of our applications, some of the other, just a few examples. So StarCCM runs really well on AWS. TLG Aerospace is a user of it. Unfortunately, the blog is almost coming out, not ready today, but it will be out in the next week or so. And what it does is that it will discuss StarCCM with EFA and FSX, and they did share some benchmarks with me that I can show. So the goal, of course, was that Siemens, the owner of StarCCM, is trying to promote is shorten time between design, configuration, and flight testing for aerospace in particular. They scale up very well. 2,000 cores, 3,000. They now have the ability for job level optimization with enhanced networking, placement groups, all the stuff that I've talked about. Workflow optimization, you can specify spot instances, run multiple clusters as TLG does, and with multiple parallel studies, you can have faster throughput. So here's how EFA runs with the C5N, with FSX and EFA, out to almost 3,000 cores. We're still getting 80% performance out against the ideal. So this is actually considered to be very, very good. Another very heavily used code, ANSYS Fluent, runs very well on us. There's a new blog out with some data on the C5 instance type, but this is an old classic standby that shows the performance of our C4 8 extra large instance, so our last generation. The blog I'm talking about is here, running ANSYS Fluent on AWS Parallel Cluster. Best practices. Again, you can probably Google this, and the preliminary benchmarks, which unfortunately are not yet available for public consumption though, are very competitive with the Cray XC50. In fact, the data that I've seen lies right on top of it, scaling out to 3,000 cores, or almost right on top of it. Okay. CFD++, it's a density-based unstructured mesh code. It uses a multi-grid accelerator. It's very well known in aerospace, not so much in other fields. This is a place where, because of the multi-grid accelerator, it actually probably is affected by network latency more than most CFD codes. And this is where we've seen a huge improvement with our elastic fabric adapter. And I want to show this slide here. And this was just kind of having fun. I don't know if the Klingon battle cruiser actually does any atmospheric flight, but we'll allow it for now. Without EFA, our elastic fabric adapter, we can see that above about 500 cores, we've plateaued. And basically what's happening here is we're taking the same problem, spreading it out over more and more cores, or more and more instances, I should say, or nodes. It's just slowing it down. There's too much communication. Whereas the blue line here is with EFA, and we see we can scale out to 1,000 cores with CFD++. This is on a 24 million cell simulation. So we really see that in this particular case, network latency is somewhat of an issue. So let's just talk about latency. Most people know of Amdahl latency, and that Amdahl's law. I mean, an Amdahl's law is such that if you were to take a fixed size problem and spread it out over more and more cores, how does that scale? Gustafson scaling is actually a little different, where instead we're going to look at how that problem scales if we increase the problem size as we increase the cores. So you double the number of cores, you double the problem size. How well does that scale? So if we look at latency, both Amdahl and Gustafson scaling are dependent on mostly non-parallel code. Parts of the code that just do not parallelize well, or serial parts, they're like, if you're reading an input file, that's going to be serial in general, although it can be made parallel. But there are parts that are non-parallel. Memory latency, that typically outside of the non-parallel code tends to be the bigger issue with CFD applications. Cache latency. There are ways to improve cache latency, which I'll talk about in another slide. All the CPUs have caches where they're trying to manipulate data or load data faster. Network latency, that is always there, although in CFD it's not the driving latency. And then storage latency. Okay, so you have to remember that latency isn't about one thing, it's about all of it. So performance considerations, if we want to improve performance, the first thing you want to do when testing AWS is use large cases. Don't come with a small case and see how does this work. Use a regular workload. Test your regular jobs, because that's the only way you're really going to see how well AWS scales. With MPI libraries, when you're running MPI, there's Intel's MPI, there's Open MPI, there's different versions, and you might want to test different ones. And within AWS, Parallel Cluster and EFA will work with certain Open MPI versions and Intel MPI, but not others. So you want to make sure that you match that properly. Domain decomposition is, I said you want to balance your workload so that you have roughly the same cells per core for all your cores. And so there might be some pre-work that has to be done to make sure that happens. In networking, you want to use a placement group, as I mentioned, and use what the fastest networking you can, and or that makes sense for you. And EFA is one example. Processor states. You can use p-states to reduce processor availability. I mentioned hyperthreading. You always want to turn that off. You also might want to pin threads to CPU cores when hyperthreading is off. And sometimes, when I mentioned in the previous slide, the cache latency can be reduced by turning off some cores. Because what can happen is if you have too many cores, they start stealing each other's cache, and then you end up having conflicts. So sometimes you actually get faster results if you take, for example, a 36 core node and maybe only run 30 of them. You might say, but I'm paying for the other 6. Yeah, but you're getting a faster result, so it really doesn't matter. So it can pay sometimes to actually run each node with fewer cores. Cost considerations. Of course, some people, maybe the runtime isn't as important as the cost. Once again, you want to test your real workloads. Things scale differently, so test the workload that you're planning on using for your cost estimation. If you're running 24/7, you might consider using reserved instances. I believe most customers save their money by the fact that they only pay for what they use, and even if they run on demand, which per core hour is going to cost more than what you might think you're used to, except you're not paying for it when it's turned off. You're not paying for it at night. You turn it off, and it doesn't cost anything. Reserved instances are only valuable if you're running 24/7, 365 days a year, and you pay for them for 1 year or 3 year increments. Spot pricing works best with small or even medium-sized runs. It may be a solution for you if you're willing to have a few jobs interrupted that you have to restart. If they're checkpointed, it's easier to restart. You just start it where it left off. Or sometimes you have to resubmit the whole thing. You want to experiment with instance types. High-speed clock might offset the higher price. Maybe your code's GPU enabled, in which case you can use a GPU. And as I mentioned before, with our partner Zenitech, who they found that they were actually running almost 1,000 core equivalent cluster on a single GPU node. Will more memory per core help? Is memory becoming an issue? And does shutting off cores help? So all of these things can enter into cost. You want to experiment with storage, local disk, shared file systems, or is an NFS storage from a head node fine? If you only have 2 or 3 nodes, maybe that's okay, and you don't have to have a managed Lustre type file system. Licensing models, and this is one of the things I want to call out specifically to Star CCM, because they've worked very hard on a licensing model that really is modeled after cloud, in a sense, pay for what you use. One of the important things with that we like to offer our customers is the ability to run many many jobs in parallel versus serially and not have the penalty of cost. Usually, if you're going to do that, it's going to cost more. If you try to get a heavily used computer and demand to run 10 jobs at once, chances are it's going to cost more. You're going to have a lot more clout. Whereas it'd be nice if our licensing model were modeled after the same ideas. And Siemens has a licensing model where you essentially pay per job hour. So it doesn't matter if you scale out. Instead of paying for core, as many licensing models do, you're paying per job. And that's actually a model that I think more and more people will move to. Okay. So we've covered a lot of things today, and some of you might have wished we had more time to look at one thing or another, but I wanted to make sort of a general overview of CFD on AWS. So we had to first cover kind of the CFD process and why AWS is useful. We launched a single node CFD infrastructure. In this case, we found an AMI, launched it from the marketplace. Again, there are many other CFD applications that have AMIs. Search around, ask if you have a contact at a vendor, ask them if they have an AMI. How do you set up? We looked at setting up a cluster to run a larger CFD applications. I'm sorry we didn't have time to do more of that. It takes a while, and so I just kind of did a quick overview. I went through some of the CFD best practices, and we talked about some CFD tools that are out there: StarCCM, OpenFOAM, ANSYS Fluent, CFD++, and there are many more. And I don't want to sell one over the other. I think it's up to your particular choice of what you want to do. So, anyways, thank you. And now we have a little time for Q&A, and I hope you enjoyed this webinar, and I hope you got some valuable information out of it. And go enjoy doing your CFD.